Hello, my name is Boaz Meivar. I'll be presenting you our work titled Evaluating Diffusion-Based Super-Resolution for Trustworthy Quantitative Metallography. This work was conducted by myself, Inbal Cohen, Ofer, Beeri, Shai, Avidan, and Oren. Grain boundaries play a crucial role in determining the mechanical properties of metals, making their accurate detection central to quantitative metallography. However, many metallographic images are of low quality, often due to limitations in imaging or sample preparation. This makes boundary detection challenging as grain transitions are often subtle and image degradation significantly reduces their visibility. Our goal is to enhance these images using modern diffusion-based super-resolution techniques while strictly avoiding hallucinations that could distort grain boundaries and skew downstream analysis, such as the estimation of average grain size via the Heyn intercept method. In this work, we show that it is possible to use diffusion-based super-resolution to improve metallographic image quality in such a way that is both visually convincing and physically trustworthy. Recent advances in generative AI, specifically diffusion models, have led to state-of-the-art super-resolution performance on natural images. OSEDiff from the paper One-Step Effective Diffusion Network for Real-World Image Super-Resolution by Wu et al., shown here in the bottom right, achieves incredible results not only upsampling the image but also adding plausible textures and fine details that match the semantics of the original low-quality image. OSEDiff is a generative model that takes a low-quality image and an additional text prompt that guides the generation process. The text prompt is obtained via a model specifically fine-tuned for this purpose called a degradation-aware prompt extractor, or DAPE for short. As a test case, we use the texture boundary in metallography dataset introduced in 2022 by Rusanovsky et al. This dataset contains relatively low-quality micrographs, making it a promising candidate for improvement via super-resolution. Using the vanilla method described in the OSEDiff paper, DAPE describes this test image as yellow sky. The generative process does improve visual quality, but on close inspection we can see the model introduces a brushstroke-like texture due to the incorrect image description. In our work, we injected a domain-specific prompt relevant to all our data in order to better guide the generative process. Using the prompt metallographic image, we see a substantial improvement in output quality, including plausible micrograph textures, hinting that the diffusion model already encodes priors relevant to metallographic imagery. Here we show some examples zooming in on the microstructural elements. This pattern is consistent throughout our dataset. We conducted a manual expert evaluation which found no significant hallucinations, added grain boundaries, or other artifacts introduced by the generative process. We also sought to quantify potential shifts in grain boundaries due to super-resolution, since grain size estimation is a core objective in quantitative metallography. To do so, we trained two identical edge detectors, both initialized from the state-of-the-art UAED model. One on the original dataset shown here on the left and the other on the super-resolved data. Here we show an example of edge detection from the two models. Red indicates false negatives, green false positives, and yellow true positives. As seen, the models produce highly similar outputs. When examining pixel-wise metrics, specifically average precision and rank AUC, we again find the models behave similarly. Here we evaluate the estimated average grain size based on the model prediction, shown here in the left column, versus the average grain size calculated using the GT annotations. The model trained on the super-resolution data clearly outperforms both the model trained on the original data and previous methods reported on this dataset. To summarize, OSEDiff, when guided by a domain-specific prompt, is effective for metallographic image super-resolution. It not only upscales images, but also introduces plausible textures grounded in physical priors. Our expert inspection found no significant hallucinations. This is further validated by edge detection probes, which showed no major boundary shifts. Importantly, grain size estimates improve significantly with super-resolution. Our data and code are freely available online. Thank you for listening.